thank you very much to be here today to this first webinar of Rossini about the explanation, dissemination of the results that we built in this European project. And as you can see, we have a pretty dense agenda. First of all, I will introduce the project itself and a vision of the overall solution that we have prepared, and starting from the architecture, the reference architecture that we had in the proposal, and then a discussion of all the core and extra components that actually make the Rossini solution. And then I will leave the floor to the actual technical developers who built each one of the different components that we will see together. Speaking about Rossini, as you probably know, Rossini is a European project done with 13 partners throughout all Europe in 7 different countries. And just in a nutshell, to get oriented, the Rossini aim is to try to overcome the conflict between efficiency and safety in the domain of robotic and then collaborative robotics. So basically, the envisioned solution with the Rossini is to build a robotic solution that is able to combine the efficiency of traditional robots with the safety of collaborative robots in a modular and scalable way. Okay, and basically this is done with solutions, technology solutions that will contain safety aware capabilities, as you will see shortly. Okay, just to start to get oriented in the Rossini solutions, I will start to explain a little bit about the Rossini safety-aware architecture. That is the architecture that we explain and we present in the proposal, and that basically has been the references throughout all the project lifespan. That is a project that is going to end the next month, so we are approaching the very end of the project. Basically, the architectures as at its core the human layer, the operators that must dialogue and collaborate with a robot that you can see as an virtual layer, and surrounding the environment with a set of sensors that allows to feed a safety controller with data that allows to generate a dynamic shell to let the robot to perform differently according to the interaction with the humans. And above this layer, there is an higher level of control that actually allows for the actual operation, like the scheduling of the activity, and the controller, like the motion planner and the execution of the robot, and along with a semantic map that allows to build the overall scene. All of these, of course, must be integrated in industrial scenario and setup. And if you already browse the Rossini website, you will see that here the solution is presented according to several layers. And this layer can be easily mapped in this architecture, starting from the sensing layer, going to the perception layer, the cognitive layer, the control layer, the actuation layer, the human layer, and obviously the integration layer. So what is the Rossini solution? What we came out with as definition after several months of brainstorm on this, the Rossini solution is, you can see it as a modular kit of components that allow to implement the safety-aware concept that I've just presented, and this component fits in different layers, covering all the 7 identified layers that I just explained to you. So, but what is a Rossini component is what we are going to see in this webinar. And basically, we have identified core components that are elements that are needed to build a Rossini platform, and extra component that instead are tools that can be useful for given application scenario, but that are not necessarily needed to build the Rossini platform. And then we have also the possibility to expand the Rossini concept, let's say, including external solution within the Rossini platform. So basically, then the idea from the exploitation point of level of the project is that core, extra, and aggregated components in sense that we can have more than one component that can be seen as a whole, can be exploited independently from the others, okay? And of course, on top of this, we can also build some services that can leverage on the component that have been built during the Rossini project. So to be a little bit more concrete, let's have a brief overview on the core and the extra components, and then I will leave the floor to the technical developers. And concerning the core components, we have a RS4 controller that basically is the lower layer of controller that is in charge of fuse all the data that come from the sensor and bringing them to the upper layer and to the safety controller of the robot. The semantic scene map, that is the one in charge of understanding the environment that surrounds the robot. The cognitive layer, namely the task scheduler. The flexible execution layer, namely the motion planner. And the scene map, the cognitive layer, the flexible execution layer, all together can be seen as an aggregated component, the control architecture. Then we have tools that allow to design a human-robot collaboration that is focused on the human factor, and a software for flexible task assignment that can give also input for the cognitive layer, taking into account the job quality, for instance, in choosing the proper path and action that the robot must do. And then we have also realized on human-robot collaborator orchestrator arbiter to take to let different HMI human-robot interface be connected with the Rossini platform. And then we also developed a virtual design tool that allows to design the human-robot cell. Moving to the extra components, instead, we have all set of sensors developed that, of course, are connected to the RS4 controller, like the vision camera, the laser, the radar, the skin. And then concerning the robot itself, we have built a Rossini collaborative robot by birth, and a safe positioning signal that can improve the safety of the robot itself, and also a conversion method to evaluate the hazard potential of cobot in free collisions that actually has also been put as part of a standard, and that allows to reach better performance, as it will be explained after. Concerning the external component, instead, we have the possibility to integrate in the platform external safety sensors, external operation sensor, external operation controllers, and human-robot collaboration selected interfaces, namely HMI. And that means that within the Rossini project, we have defined or start to define possible interfaces for all these kind of devices. And recalling the fact that we can have also services based on the ROSSINI Modular KIT. These services, the main services that we can think of are the job quality evaluation service, selection of suitable human-robot collaboration interface, professional service to evaluate the hazard potential, and obviously at the very highest level, the Rossini platform integration as a service. Okay, so what I didn't say so far, explain so far, is what a Rossini platform is, and we can define the Rossini platform as an aggregation of core all the core components that I presented an extra component as a set of interconnected elements. And obviously this covered all the layers that I've already presented you. And the next step would be to add, to suitably configure this component, add possibly external components for realizing given application scenario in robotic. And in the Rossini project, we had 3 use cases: the Whirlpool, Schindler, and the EMA use cases that will be part of the next open webinar, for which I've already invite you, and to save in the agenda this fact. This will be held at the end of March, and will present the overall results that we reach in this scenario, in these use cases. But for the moment, I will leave the floor to the technical suppliers, starting from Gildo from Data Sensing, that will present the technology of the sensing technology of Rossini. Thank you. Gildo, and the floor is yours. Thank you.
So I'm Gildo Andreoni from Data Sensing, and so now we are going to talk about 3 components of the RS4 of Rossini, which are the RS4 controller, the RS4 Vision, and the RS4 laser. This is the architecture that Riccardo showed before, and the RS4 components, that RS4 stands for Rossini Smart and Safe Sensing Systems, are developed inside the work package 3 of the project. And the main aim is to combine a set of sensors that can be also from different technologies in order to reconstruct a monitored area using a sensor fusion. And the reconstructed environment will be used to limit the speed, for example, of the robot, or stop the robot when an hazardous situation can occur for the human. The information generated by the safety sensor could also be shared with another layer, which is the outside layer in this image, that can take advantage of the fused information to generate better trajectories for the robot, for a task accomplishment, or for maximize the behavior of the robot. So this is the connection diagram, I would say, and on the right we have the RS4 system controller, which is a component that is in charge of collecting the data from different kinds of sensor. For example, on the left we have the RS4 Vision sensor, which are 3D cameras that we developed from scratch in the project in Data Sensing, and can be connected up to 4 to the RS4 system. And also the data coming from multiple laser scanner, up to 4 laser scanner, can be acquired by the RS4 system. This RS4 system controller can be connected to the robot in a safe way to limit or stop the robot when hazardous situation occur for the human. Also, other sensors can be connected that are the one described by Matthias before, that are the RS4 Skin and the RS4 Radar, but are not part of this presentation. So the safety in collaborative robotics. Basically, what we implemented in our controller are some of the modalities that are described in the ISO TS 15066 that describe the safety function of the robot that can be collaborative or not. So the first one is the simplest one, and is a safety rated monitor stop. Basically, what happened is that when a human enter in a forbidden zone, the robot will be stopped to ensure the safety of the human. A more advanced modality is the speed and separation monitoring. That is the one that we can use for change the robot speed according to the distance between the human and the robot, to ensure that a collision will never happen between the human and the robot, because we have time to stop the robot in time. And another modality that we can use is the power and force limiting. So this one can be used, for example, if we have a collaborative robot. So we have the ability to switch the robot in a collaborative mode. In that case, a collision is can happen, but will not be hazardous for the human, basically, because the force is limited. So this is the behavior that we have implemented. So in the diagrams on the right, we have on the x-axis the distance between human and robot, and in the y we have the maximum speed allowed for the robot. So as we can see, higher is the distance and higher is the maximum allowed speed. But the behavior that we have that we can implement if we have a non-collaborative robot is different than the one that we can implement if we have a collaborative robot. For the non-collaborative robot, there is a threshold distance, I would say, that actually says under this distance between the human and the robot, you have to stop the robot. So go to a safety rated monitor stop. Over this distance, you can increase the speed of the robot depending on the distance between the human and the robot. On the other side, with a collaborative robot, under that threshold distance, we can switch the robot to a power and force limiting mode. So we can allow the robot to still move, also if lower speed and with lower force, until the touch occurs between the human and the robot. So about the minimum distance calculation approach that we have. So it's pretty different from the one that is used by the safety sensor on the market, because currently, actually, the minimum distance that we need to take into consideration is the one defined from the human to the reach of the robot, so which is larger of the volume occupied by the robot. So this give you a lower minimum distance between human and robot, and so a lower allowed speed. With RS4, the approach that we are trying to use is to measure both the position of the human and the robot, and so time at runtime. So we will have a lower minimum distance and a higher maximum allowed speed. So the first technology that we have developed is this RS4 laser. So it's based on the data sensing safety laser scanner, and we created it fusing multiple data coming from multiple laser scanner, up to 4 laser scanner. In this way, we can reconstruct a 2D map of the environment. And in this case, on the left, we can see a video of a human, for example, working on the monitored area. And in this way, fusing multiple devices, we can solve the occlusion that can happen, if, for example, if an object is placed on the scene. Another device that we developed, which is probably the one that requires more effort, is the RS4 Vision. So those are 3D cameras that can be placed in the working environment, also more than one, so up to 4, in order to enlarge the monitored area or to resolve the occlusion that could occur. So this is these devices is developed taking into account the ESC 61496 that actually describe how to create a 3D camera to be safety compliant. In the image, we can see that so the robot is recognized as a robot and labeled with the purple color, and the human is recognized as human and labeled as with blue color. And the minimum distance that is measured is the line that we see in the image. And what about the RS4 system, so the RS4 controller? So is the component that can collect the data from different kind of sensor, multiple sensor, and fuse it together in a single map. So on the right, we see, for example, the dots on the floor, which are the 2D map reconstructed by the RS4 laser, and is placed in the same scene of the 3D point cloud generated with 3D cameras, so the RS4 Vision. And in this way, we can define the behavior of the cell using multiple kind of information. And here in the RS4 system is where we have implemented the speed and separation monitoring, the safety rated monitor stop, and other advanced functionalities. And this component can be interfaced with the robot using a safe interface, and the generated data, so the processed data that we can see on the right, but also the raw sensor data can be shared with a second controller, which is not safety related, and can use this information for example, for AI or object recognition or other tasks that are not safety related, but useful for define the behavior of the cell. So I guess that's all. Thank you very much.
Thank you very much, Gildo. Okay, so we can move on with the agenda. If Matthias from Pilz is ready to present.
So my name is Matthias Schweiger. I'm from Pilz, and we had the 3 tasks: RS4 Radar, RS4 Skin, and the safe position signaling. So let's start with the radar. So in this task, we had to evaluate the radar technology for a new kind of a 3D safety sensor. We always kept in mind to do a safety concept. And radar has advantages in the human versus object recognition. So we evaluate this topic too. And we implemented a ROS and a UPC-UA interface to speak with the RS4 controller. So first of all, we had to learn what to do with the raw point cloud data. So from noisy point clouds, we had to develop algorithms to get clustered and filtered objects like the one on the right. Then we can calculate a center point of intensities. And now with that point, we could calculate the directions and velocities of objects and humans. So the bottom right picture is a small sample application, where at the bottom is a safety application and the point is a human, and we can calculate and see the direction of the movement of the human. So goes the human in the direction of the hazard or not. So here a few results. We tested the sensor with a walking and standing person. So the person walks from 1 to 2.2, 2.3, and so on. And you see the velocity of the person goes up and down, and you can see the distance to the sensor gets lower. So we demonstrate our radar sensor, this time in a white housing at the EMA use case. There it supports the safety and measure some point clouds to the RS4 controller from data sensing. So the next task was the RS4 Skin. This was a safety soft skin for the human-robot collaboration method 4, pressure and force limitation. And the advantage is the fast reaction time. So we started with very simple shapes and tested it in our Pilz manipulator. Then we can see it in the block diagram. We could use a Pilz product to connect the skin and connect the robot or the RS4 controller via output, 24-volt safety outputs. And then we showed the skin in the whirlpool use case. Therefore, we have to examine different soft materials. We had to find the right force threshold to determine the activation force. And we 3D printed the gripper of the whirlpool use case and had to develop the 3D shapes of the skin. So Yeah, all right. Then this is the result for the skin. The line on top, it's the force limit of the TS 15066, and the red line is the universal robot without a skin with the internal torque sensors. And if we use a skin, we could run the robot 2 times faster. So because of the fast reaction time, we are able to get a higher robot speed. If so we can improve the application in terms of speed and cycle time. So another task was the safe position signaling. That's the name for a solution where we add safe speed and safe position safety functions to a robot manipulator without these safety functions. So the test implementation of the solution was with the PILS component. So we had the PILS robot manipulator and a non-safety robot drive. And we added the RSCU, it's named Robot Safe Control Unit, to calculate safe speed and safe position monitoring. So what we did, we had to add a dual channel communication through all the joints and a dual channel encoder architecture to get the position data out of the robot manipulator in a safe way. So we started the hardware based on a safety card for 1-axis drives from PILS, and we developed a new firmware which was adding several safety functions for the axis, like safety limited position and safety limited speed, and for the whole robot, so we can monitor the TCP position or the orientation, the tool orientation of the robot in a safe way. So we had a small demo where the light curtain on the right triggers the monitoring of the robot, and if the robot was moving in the red area, it was moving slow with monitored safe speed in this safe position. If the robot was out of the left, it could run full speed. So I'm at the end, and if you have any questions, feel free to ask.
Thank you very much, Matthias. So it's now the time of Martin from IRIS.
Okay, hello, I'm Martin Folger from IRIS, and I will talk about the semantic scene map. As we've seen in the introduction, Rossini has several layers, and the semantic scene map is in the perception layer between the sensing layer and the cognitive layer. The sensing layer, in this case, what is relevant for us are the cameras, the RS4 cameras, which provide, in this case, gray images, and they also provide depth images, which we need as input. Then the semantic scene map performs an object detection and separately a human skeletonization algorithm. And it also uses the depth information of the cameras to place the detected objects in a 3D. Whereas the algorithms work in 2D, the result will be put in 3D using the depth information. The result of this will then be passed on to the cognitive layer. So here we see this as an example. So the object detection is this kind of algorithm which recognizes objects in the scene and places a box around it and labels it with the thing that it has detected, in this case, person. The skeletonization algorithm works a little bit differently. It only works with persons, and it not only detects it's a person, but it actually detects the human skeleton, the joints, as you see at the bottom left. On the right, you see this both combined. The yellow is the box, and the skeleton you see as well in 3D. Here the limbs are made thicker, but this is just a way of does not come from the algorithm, but it's just a visualization thing. Okay, now this is about how this is actually implemented. So in Rossini, we use the ROS operating system, the robot operating system, which allows you to have lots of different software nodes, which are independent software computer programs which read information from the pool of topics and then process them and create their own ROS topics, which is again a data stream which can be subscribed to by subsequent programs and for further processing. So in this case, at the bottom you see camera 1 and camera 2. This is just an example. It could be 3 cameras or 1 camera. So you can have multiple cameras. Each of them create and publish to the ROS network, to the ROS framework, grayscale images, depth images, and much more like camera information. There's a huge number of ROS topics, which is published to the network. The 2D skeleton is one of these algorithms that I explained before, which reads the information it needs, mainly the grayscale images at this stage, and applies the algorithm, and then publishes various topics. For example, it publishes the same image again with the skeleton superimposed. This is only for visualization, but it also publishes the skeleton as a number of coordinates, as a list of coordinates, and publishes into the ROS for further processing. The same happens with 2D object detection, and the same happens then again for the camera 2. The next step is the 3D skeleton and 3D object detection nodes, which subscribe to the 2D information already obtained. They subscribe to the depth image and place the 2D coordinates into a 3D scene and publish that information again in the ROS framework. This allows for the results from different cameras to be fused into one final skeleton or object detection box. This final result gets published and will be used by the cognitive layer, or also it can be used by the visualization of ROS to inspect the results. Okay, here we have an example from the Schindler use case. This is a test scene of the Schindler use case with a human being working on a elevator button panel in collaboration with a UR10 robot. So here you see the skeletonization applied. On the next one, you see again the skeletonization applied, and as I said before, through publishing the skeleton and then further processing it, in the end you see this final result. This is the 3D human skeleton. And again, as well, a 3D representation of the robot. The robot information in this case does not come from the cameras, but it is actually reading the robot coordinates directly from the ROS framework. The robot positions are also published as information in the ROS framework. This can be then be combined in the 3D scene to give you this final result, which is what is being used by the cognitive layer. And here you have a similar example, but instead of the skeletonization, you have the object detection algorithm detecting a person, the UR10 robot, and the elevator panel. And this is the whole final result, also represented here as the yellow box for the object detection. This would be the person box. Inside you see the skeleton. And here you see 2 or 3 frames of reference, the world frame of reference, which is used to publish this final result. But initially the skeleton and the box are calculated in the reference frames of the cameras, and they have to be combined into a world reference frame, which is then used higher up by the cognitive layer. Okay, this is all from the semantic scene map.
Thank you very much, Martin. And now it's the turn of Christian from Unimore that will explain us about the controller.
Hi everybody, so I will talk today about the cognitive and the flexible execution layer and the orchestrator. So these are 3 of the core components of the ROSSINI toolkit, as Riccardo perfectly explained at the beginning of this webinar. So This is a part of the overall ROSSINI architecture that focuses on the interconnection between the orchestrator, the cognitive layer, and the flexible execution layer. So at the bottom, we have the meta sensor for the ROSSINI architecture, which is the semantic map that, taking information from sensors, from the position of the human and from safety by the RS4, it builds a representation of the world that will be the main input for the cognitive layer. The cognitive layer is basically the layer responsible for dispatching tasks between the human and the robot, and takes as an input the job description and the job quality indicators that we want to exploit for maximizing the quality of the job, and it takes as an input the output of the orchestrator. The orchestrator itself is basically an object that coordinates the communication media the human can exploit for interacting with the robot. So the human can talk with the cognitive layer, as we will see later, through several means, mic, graphical user interface, whatever, basically, and the orchestrator will transform this in a message for the cognitive layer. The cognitive layer outputs a set of tasks for the robot, and these tasks are physically executed through the flexible execution layer that plan the motion and the actions that the robot has to do. So let's try to describe quickly each of these ingredients, okay? So let's start from the cognitive layer. The cognitive layer is basically made up by two tasks, two blocks, the task assignment and the dynamic scheduler. The task assignment takes the description of the job and it splits it into a set of tasks. And as I said a few minutes ago, it distributes these tasks among the human and the robot according to a set of metrics that evaluate if a task can be done by the human, if a task can be done only by the robot or only by the human, and it evaluates how good are humans and robots to execute a specific task. And then this dispatching is made based on nominal information. I know that the human takes I don't know, 10 seconds for doing task 1 and 20 seconds for doing task 2. And of course, this information is a nominal information, but as we all know, there is no nominal human. Each of us is different. So I may take 12 seconds, I may take 30 seconds, I may take 2 seconds. So this nominal information are used for building a task list that is sent to the dynamic scheduler. The dynamic scheduler takes as an input the real monitoring of the human. So there is through a sensing system, it's possible to evaluate online through an algorithm we have exploited and integrated in the ROSSINI cognitive layer, how much time the human is really taking for executing the task. And the dynamic scheduler dynamically changes the order of the tasks, and it can even assign one of the tasks nominally assigned to the robot back to the human, or a task assigned to the human to the robot based on what is really happening to what is really happening in the scene. Okay, so the output of the scheduler is a sequence of tasks to be sent to the human and to the robot, and the sequence is dynamic. Okay. So this is, just to give you an idea on how we solve the task assignment problem. It looks a nasty problem. It's of course an optimization problem because we want to optimize. I don't want to go into the math. I just want to show you basically the structure. Basically, we want to ensure precedence constraints are satisfied. So if, I don't know, I have to place a screw before taking the screwdriver, for example, and not the other way around. Okay, and these final constraints are the job quality constraints that we integrate with the help of TNO in order to ensure that the job the human is executing always satisfies a desired set of a certain level of quality, basically. So the task assignment uses weights for understanding what has to be given to the human and what has to be given to the robot. It minimizes the effort and the cycle time and it ensures a maximum effort over the entire work shift, and it provides a nominal schedule. And the dynamic scheduler introduces in a human-robot collaboration cell, which is super dynamic, the awareness. So given the awareness on how much time the human really takes for executing the task, it reschedules the activities in order to maximize the efficiency of the overall procedure while preserving a certain level of job quality. And of course, the human can communicate with the robot because, for example, I may be very skilled in executing a certain task that is nominally assigned to the robot, and I want to tell the scheduler, hey, I want to do that, and the scheduler rearranges all the tasks in order to provide me with the task I want to execute. Okay, so this is a simple example for showing you what's happening. I hope here it comes. So this is the nominal schedule of a job. This is Andrea, actually the one that developed most of this. Okay, so the robot is executing this nominal task. And at a certain point, this is the algorithm I was mentioning to you, that is estimates the real time expected for executing a task on behalf of the human. And since it seems that Andrea is a little late with respect to the nominal time, well, the dynamic scheduler schedules another task for the human and for the robot. Okay, so the robot can move ahead and take one of the tasks. Okay, for the sake of time, we'll move forward. I'll be happy to show you the rest of the video later if you're interested. Okay, so once the tasks are assigned to the robot, sorry, it's important that the robot plans a trajectory for executing them. And this is the role of the flexible execution layer that takes care of planning the best dynamic trajectory. Again, dynamic, because in the robotic workspace, there is a very dynamic object, which is a human. Okay, so we need to take care about the human to consider safety constraints, and we use speed and separation monitoring for that. So again, the flexible execution layer is made up of a couple of main blocks: trajectory planning and trajectory scaling. The trajectory planning, given the information about the world provided by the semantic scene map, plans the best trajectory online for understanding, for achieving its job. And given the information coming from the RS4, the trajectory scaling tries to adapt the velocity of the robot, the velocity by means of which the robot follows the trajectory in order to meet the constraints given by the ISO 15066, so for achieving a safe motion. Of course, it may happen that in order to achieve a safe motion, we need to go too slow, and you can set a threshold. And when the robot keeps on following the desired trajectory with a good speed for speed and separation monitoring, but we understand that, hey, the trajectory I planned a while ago is not good enough, so maybe it's better to replan the trajectory in order to achieve better performance. Okay, so it's an integration between velocity scaling for ensuring safety and replanning when needed in order to ensure optimality. Again, one of the goals is always efficiency, the main goal actually. So a few information about the trajectory planning. For those of you who are familiar with that, we have used the RRT Connect algorithm, which is super cool and super fast. And we have exploited path velocity composition for controlling the velocity by means of which the robot tracks the desired trajectory. And we have integrated the ISO 15066 regulations in order to find the best velocity. And again, all in all, we have built another optimization problem, which is convex, for those of you who are familiar with that, which means that it looks nasty, but it can be solved in milliseconds. Okay, and so it can be, we have implemented it in real time, so the algorithm has been solved in real time. Okay, so again, short video for showing you how it works. So this is the robot planning its trajectory. So we did these experiments on the Pilz robot, which is in our lab, currently thanks to the builds. So Andrea comes in, and the robot sees Andrea, and it reduces the speed, scaling the speed the trajectory is tracked with. And again, okay, it takes too much time. Why not replanning? It seems that Andrea is staying. And you see, it stays too much on the same position. And I want to conclude by introducing the orchestrator. The orchestrator is this nasty guy. Okay, basically it's a ROS interface for all the interaction devices we have used in Rossini in one of the use cases. So we have the projector, the touch screen, the microphone, the speaker, and so on and so forth. And all these devices are integrated with a standard ROS interface that allows to integrate any device with ROS. And ROS and the information coming from these devices is arrives to the arbiter. The arbiter is nothing else than a strategy, arbitrary strategy that you can choose for handling priorities between the devices. Maybe you want the projector to have a higher priority with respect to the speaker or whatever. So it's really application dependent. And it dispatches the information to the dynamic scheduler, to the robot, or to the RS4. Okay, so this is basically it. So again, for the sake of time, I don't want to go too much into detail. Again, I'll be happy to talk with you about this later. And this is it. So I hope I was clear, and I'll be glad to take any questions.
Thank you very much, Christian. Perfectly on time. And I will move to Mattia from SUPSI.
I'm very honored to be here to present you our part of the project, which is the collaborative robot which we designed. So okay. So I'm gonna tell you everything about the robot that has been designed, which has been defined since the very beginning as collaborative by birth. And this is something that I will explain in a few words later. The content will be very dense. We have many things to show, but we will go through about pretty much everything, but very fast. So fasten your seatbelt. Okay, here we start with the highlights, just in a nutshell, what this robot can achieve. So in terms of specs, main specs, you can see the reach is about 1 meter. The robot has been designed with a 15 payload goal. The position accuracy, thanks to the vast amount of the encoders, is fairly high, so it's 0.05 millimeters, and the speed is up to 1 meter in very specific conditions. And then I'm gonna present you the main features, which are this dual operation mode, collaborative and industrial. I'm gonna talk about the high joint sensitivity. I will explain the hybrid braking system, allowing the robot to achieve these performances. And then I will mention about the capacitive sensing system on the joints, and eventually the cherries on the pie about these advanced interaction capabilities that we included. So here, very briefly, you can see the design, overall design of the robot, the sizes, and so not much to say here. In this sense, it is quite a traditional design with 6 axes and the links needed to connect all of them. Okay. When it comes to the operation modes, here is probably where we make the difference with what's available currently on the market. With the robot that we designed, we essentially have two operation modes. One is industrial and one is collaborative. And what is peculiar about the robot that we designed is that we are able to seamlessly go from one to the other, and the operator essentially does not even notice that. And this is triggered by several different kind of events or scenarios, and which are mainly related to the robot itself and the human operator. When it comes to the robot, it depends where the robot is located, for example, the operation it is performing, the distance from the operator. And when it comes to the operator, it depends on what the operator is doing. And it also depends on the skills of the operator, the age, and much more. Because you can imagine that there are mostly, as anticipated by Christian in the previous presentation, the human operator can be very, very different. So it can be very fast, very skilled, or can be a rookie starting to learn his way into the operation he has to do, and the robot needs to adapt to that in order to be as efficient as possible. The design, just a few words about the core essentially of the joints. It is composed by a torque motor, which is hollow, is made by a stator and a rotor. This allows the cables to go through it and make a very clean design. We do have harmonic drive gearbox, which is essentially zero backlash, and so it is very accurate and provides very high ratio within a very compact form factor. We have a double encoder solution before and after the gearbox, which provides very high accuracy in positioning and in the ability to detect anything which is happening to the robot. We have a brake solution, which I will go into more details on the next slide. And then it's important to see that all the electronics is embedded within the joint itself. Okay, 2 words about the braking solution. So we came up with this design, which we thought was the best. You cannot just choose a solution and use it everywhere in the robot. That would not be efficient, because the bigger joints have specific requirements and the smaller joints have different requirements. So that's why for the 3 bigger joints, we did use a hybrid solution in which we use the, let's say, more traditional electromagnetic spring-loaded, essentially, type of brakes. But we combine that with an electronic type of braking system, in which essentially, as soon as an emergency event occurs, it will immediately short the coils within the motor. And this will immediately start the braking. And then as soon as the electromagnetic, which has an inertia because of its mechanical nature, kicks in, then this will complete the braking. For the smaller joints, we go for a more traditional mechanical type of brake with latch module, which makes it very, very small and light. Okay, 2 words about the electrical design of the robot. We do have a bus going through all the robots, and the single drives are connected through Ethercat. The tiny drive is very, very powerful with a peak power of up to 60 amperes. And we use very special cables, very flexible, in order to be able to go through all the robots without any issues. Okay, this is the final look of the robot. And here, a very basic demonstration. You can see the robot moving, performing some pre-programmed sequence. In here, you can see standard Cartesian moves, essentially showing a little bit of everything it can do, the speed and the agility, and so on and so forth. Okay. When it comes to the advanced features, we did include hand guiding, so essentially the operator can take the robot and move it by hand. And on the right-hand side, you can see the gripper control is essentially a double click or double tap feature that is very useful when you perform hand teaching of the robot. You don't need to push any button, just double tap on the end effector itself. When it comes to the teach mode, that's actually a quite long movie, so I'm gonna just start it and then move to the next one. You can see how the teach mode would work. On the right-hand side, you can see the collision detection feature, in which when the robot is moving, if somebody touches it, it immediately detects it and stops the robot. Okay, 2 words about the capacitive skin that we are planning to integrate in the robot. In here, in this movie, you can see its effectiveness, so that when somebody approaches the robot with a distance up to 25 millimeters, it is able to detect it and prevent the collision in the first place. Okay, and here the cherry on top, we included a very fancy feature which we have not seen before. So what we did was to include and embed into the end effector essentially the ability to have communication with the operator through an interactive display. This is a flexible OLED touch display, very high resolution, which allows to essentially display anything. Also here, I have a small video showing the robot in action. Everything is in development, so all what you can see is being updated essentially daily with new features and new functionalities, and allows really to do a lot. On the one hand side, during the operation, during production of something, it clearly shows the operator what is going on. And concurrently, also during the teaching phase or so, it displays a bunch of information, graph, stats, and very, very useful type of information. We also have included voice commands within the robot, which is also something new, mostly when it comes to the industry standards. Here, just a brief slide to show that the graphics design is also going on. And the last slide is about the safety certification process that we are currently going through in order to get a final certification for the robot. And with this slide, I thank you very much for the attention, and questions are more than welcome, either now or later or whenever you want. Thank you very much.
Thank you very much, Mattia. Then we can move to Frank's presentation from TNO that will explain us about human factor.
I would almost say, and now for something completely different. So we're talking about the human factor in human-robot collaboration. And why is this important? Well, I think that it's, wrong one. I think we shouldn't forget the H in HRC. And why is this important? Well, I don't want to dismiss any technical challenges because they are enormous, but because they are enormous, the human in the technological development can easily be forgotten. So this project is about safe technology, and this is extremely important. I cannot stress how important that is. However, when we think about safe technology, we should also think not only about impact avoidance, but have a wider human perspective. So it's also about trust and safe feelings. But not only that, the technology should be workable. So you should be able to read the robot as a human. So it should react predictable. You should be able to communicate with the robot, as Mattia just explained about about this interface. Because the human should stay in control. You shouldn't become the slave of the robot. And it should improve work, for instance, reduce physical loads. So in general, the human layer is also there, or what we did is also there to, because any change is an opportunity to grow, and also in the field of job quality. And this is also a European requirement, which you will see in proposals. Robotics and AI developments should not only benefit productivity, but also job quality. And this has been our role in the project. So if you talk about human factors, what did we do? Well, first of all, we created a design tool to help structure the design process when you are introducing a collaborative robot. A task planner has been developed together with Unimore. Human-robot communication. How do you communicate with the robot? There are several design issues where we helped out, and in the end, this is something we're still going to do: evaluate the effects on job quality, or at least parts of job quality, because a robot cannot affect every aspect of job quality. This is the design tool where you have several panels. There's a task panel. What are the robot and the human going to do? We have several steps in it. There's an information panel and a parameter panel. And these are the steps. So everything starts with a proper description of processes and tasks. You define task allocation scenarios, who's going to do what, select job quality evaluation parameters, and score the job quality evaluations parameters, and the system also visualizes the results. There's an important point about this, that's to stimulate discussion about the changes you are going to do. This is something that's in ergonomics is extremely important. User participation, discuss about the changes you are going to do. Now, this is, for instance, the analysis of tasks and how you build scenarios. So you list the task, you list task durations in the system, and you assess these subtasks on physical loads, on cognitive loads, psychosocial aspects, and environmental aspects. So you do this before, not after. And then the tool is able to visualize the sequencing of robot tasks and human tasks. Here you see two examples, and if you show them after each other, then you will see that in the second scenario, there's a lot of waiting time, either for the robot and the human. Well, the robot is very patient. He won't mind any waiting time, but the human hates waiting time. Some waiting time is very functional, as in a micro pause, which to recover. But in general, if you introduce waiting time for the human, you will create behavior you may not want from the human. So it's important to avoid this waiting time. And then in the end, the tool allows you to visualize the job quality in certain graphs. I won't go into detail. Then there's the process management tool, which Christian from Unimoda explained, and it monitors the human and the robot tasks, and it allows flexible task assignment. And this is exactly what you want in a collaborative setting. So it adapts tasks depending on monitoring results, and it limits sets. For instance, it limits heavy lifting, it reduces waiting time, it allows recovery, it reduces exposures to risk, just like you have set in the system too. Very important, give the operator control, because this is one of the most important aspects in job quality. An operator needs to have a certain control, and this is, for instance, in the EMA use case where we have you have flexible task assignment. The operator may receive a task from the system but not be ready to perform this task, and then the operator can tell the system, I'm not ready for this task, I decline the task, or I have done the task, I'm going to do the next task. So there's an ability to communicate with the system and to tell and to ask the robot to do certain tasks. Very important. In general, when we talk about this, this is generally how I experience as an ergonomist. When it's about technical systems, then you see a system optimization focused on the technical part, but the operator is also part of this system. So this system should also be optimized. This is what we did in the Rossini project, and we stress that you should also look even larger, to look at the big picture, because this is the full system that you want to that needs to operate in a perfect manner. And this is exactly what we call ergonomics, which leads to sustainable productivity. And this is exactly what you want. And with that, I thank you, and we can go on to the next speaker, and questions can come afterwards. Thanks.
Thank you very much, Frank. Perfectly on time. And now it's time of Roland from UFA that will explain us about the evaluation of hazard potential and free collision.
So I want to talk, or want to give you a short overview about what we have done regarding evaluating the hazard potential in free collisions. So what we did in the Rossini project was we developed a conversion methodology which allows us to evaluate hazard potentials of cobots, and especially here in free collisions. So what we have right now is on the left side we can distinguish between two contact types. So we distinguish between crushing, which means that the robot is pinching the human body part at high speed. And we also have the case impact, so meaning that we don't have any clamping. The body part is moved to free. We don't have any spatial constraints. Okay, so we don't want to, today I don't want to talk about pinching, so clamping, because this is a special type which is solved. So there are no need for any improvements. So what we see in the middle of the slide is a very simplified model for these kinds of contacts. So crushing means we have the robot which is moving with the mass against the body part which is affixed by an obstacle. Okay, and what we would receive for these states, so let's assume the robot has a velocity of 250 millimeters per second, and let's assume it has a weight of 15 kilograms. Then for the case of contact at the lower body, again, I guess it's a forearm. Here it's a forearm. You can assume a stiffness of 40 newtons per millimeter. We will receive the red curve seen here on the right, plotted here on this diagram. So, and for the free impact, so meaning that we don't have any special constraints here, drawn in blue at the bottom of the slide, we will observe a completely different contact force plotted over time, here depicted by the blue curve. So we have the same, exactly the same states from the robot, but just a different condition, and of course, and it's obvious we will receive a different force. And what we can see is that the force is reduced by 43%, and this directly translates into a robot speed, which can be increased by 2.9 times. And then we still do not exceed the force we observe in crushing. So both contact types have a significant different dynamics. Okay, that's just as a background information. And now we come to an essential limitation. So when we are doing this measurement, we can only measure this case, so crushing. So even if you want to assess the transient case, we cannot do this today because this measurement device, which we can see here on the photograph, it must be a fixed to rigid structure in order to ensure that we have a certain repeatability and a certain accuracy. So you cannot hold it by hand because this will change the stiffness configuration. It will definitely definitely very difficult to have to receive repeatable results. Okay, so again, what we want to assess is this one, impact, so transient contact, but what we can measure is only crushing. So the case where the body part is restricted in terms of its motion by an obstacle. Okay, and the consequence is, of course, please keep in mind that we have a significant difference here in terms of the contact force and the speed, that we will receive, of course, lower speed than we should, lower speed that we could have when we have a real transient case. So the speeds are artificially reduced because we cannot measure it. Good. So this is the current state. And what we developed in the Rossini project was a conversion technique, actually. So again, we have these two contact types, transient and quasi-static. Okay. We have already seen this, and we can distinguish the transient part into crushing and impact. So we can measure the crushing contact, and what we want is we want to have a result for the impact, which we cannot measure. And here at this, so here. This is exactly what we did in Rossini. So we developed a conversion technique which allows us to transform the results received from a crushing into the case which will, or into the forces which will reflect the impact case. And this comes, or this works, or this bases on 3 steps. So the first one is that we need to determine the effective robot mass and also the effective body mass. So the effective mass of the body part which is affected by the impact. Then we can calculate a reduction factor which reduces the measured maximum force from the crushing case into the case that would reflect the impact. Okay, and what we need for that is here, keep in mind this model, we need to calculate, of course, the reduction factor. We need to calculate or determine the effective robot mass, and we also need to determine the effective mass of the human body. Good, this is the approach. And this is our solution. So we are here in the photograph. So we're doing this measurement. We receive a maximum, or we receive, or we measure a force over time. Okay. So here illustrated on the left side from the slide, and what we can do or what we can derive from the force signal is we can estimate very easily effective robot mass. This is, of course, not 100% precise, but it will give us a conservative estimation. So we overestimate the robot mass, which is good because this gives us a margin that is conservative and will not lead to an underestimation of the contact forces. Good, we have this. And what we need also is the effective body part mass. This is much more complex than this one here. So because the mass of the effective mass of the human body depends on the contact points location, on the direction of the impact, and on the body posture. So here for that we need a model. And that's why we developed the Rossini human body model, which gives us exactly what we need, the effective mass for different body postures for different locations and so on the force. Then we can very easily calculate this reduction factor. So we confirmed an experimental experimental tests with different cobots, that this factor allows us to precisely transfer the contact forces from a crushing case to an impact case. So by simply multiplying the maximum force by the reduction factor, and this will give us an equivalent impact force. Sorry, you cannot see the symbol here because it's drawn in white. So here should be an Fmax with a star. And the good thing is, this is, I would say, a huge success for the Rossini project. So this methodology will be also included in the ISO PAS 5672. This is an upcoming normative deliverable from ISO, which will set the requirements for doing these measuring, these tests, this collision tests with robots. And what's really an advantage for us is I'm the convener of this working group. So it's IC TC299 working group 8. And we are working currently on this project. And this was a good opportunity for us to bring this also in. And this was accepted so far, but it's not yet published. There is still a ballot which we need to take, but there's great potential that we will have it published by the end of September this year. Good. Back to the human body model, just a brief overview. As you can see, it's a multi-body system with a lot of center of gravities, links, joints, and so on. And we use this model to calculate the effective mass of the human body model. Of course, we can use, or we can apply different body postures. We can apply different impact directions or different contact points and so on. The good thing here is that this model will be published, I hope soon, at the Python lab, which will be then available as open source in GitLab. So everyone who's interested in using this model, you can download it, use it. But we still need to figure out which license model which license model we need for this kind of open source. Good, and just a brief overview of the potential. So this curve is very easily to read. So here we have the impact velocity taken from measurements with real collaborative robots. Here on the right side, on the y-axis, we have these. Actually, on the left side, we have the maximum impact force and measured with a pressure force measurement device. And what we obtained from the test is the green curve with a fixed device. So the green curve represents exactly what we will receive today because we need to fix it. And then we did some test with the movable device. So we will receive the red one if the device has a weight of approximately 23 kilogram, and for 7 kilogram, it's the blue curve. And what you already can see here is that we will observe a significant increase or decrease of the forces, increase in velocity if we make the PFMD movable. But movable means more effort, which needs to be put into these measurements. That's why we want to go with our conversion technique. And here we compare the results to our conversion technique. So again, we have the green curve taken with the fixed measurement device, and with our conversion technique, we will receive the red curve, which will give us, at least for this case, for this condition, an increase of 26% in velocity compared to the 32, which we will receive with the movable device. So we are a little bit below what is actually achievable with a movable device. So here, this shows us that we are underestimating the speed. So we are on the conservative side, which is good. And for the blue curve, which is 7 kilogram, we will receive an increase of 73% compared to 100%. It's approximately the same relative difference. So in short, in summary, the conversion technique will allow us to go even faster when we can ensure that we have transient contact. That's everything from my side. And yeah, if you have questions, then please, I hope that we have time after the presentations to answer them. Thanks.
Thank you very much, Roland. So we can conclude the presentation, coming back to Martin, that will explain the virtual design tool that actually may wrap up altogether the components that we have seen so far.
Okay. Hello again. So now we'll talk about the virtual design tool. So the virtual design tool is developed on the basis of the program VRAP, which is a robot simulation tool. So here you see some examples from the three use cases. On the top right, we have the IMA use case. On the top, on the bottom right, the Whirlpool, and on the bottom left, the Schindler use case. So what you see here is basically the normal VRAP functionality. You can create virtual scenes with the machines, robots, walls, cameras, and workers. Additionally, you can visualize, for example, on the bottom left, you can visualize the actual field of view of the cameras, or you can mark certain areas as collaborative areas, which we have done here in orange and lila. Now we added the Rossini specific functionality to this VRAP tool. There are basically ways that you can extend the functionality. You can use the internal VRAP scripting language Lua, or you can also write C++ plugins that can interact with the workspace in this virtual scene. So here you see, as an example, the Rossini custom GUI. With the first functionality tab, is the camera functionality. So you can switch on and off the cameras. So what I have to say is all these virtual scenes you can actually simulate by starting the simulation. Then everything starts moving. The robot starts moving, the human starts moving, like in a real scenario. And this moving scene can be filmed by a virtual camera. And this you see here on the right, it's a camera image in grayscale produced by a VRAP camera. This is also an example of how you can interact with software outside VRAP. It allows you to publish these camera images via ROS, and then you can apply what I said earlier in the other presentation about the semantic scene map. You can actually test the semantic scene map software on these simulated images. And here we see an example of the object detection algorithm applied to the simulated images. Here we see more examples of the functionality that can be controlled by the Rossini custom user interface. First, we have the robot movement panel. You can either start moving this robot by using the Lua internal scripting languages of VRAP. So if you hit start, it will move according to a trajectory which you define inside that Lua scripting language. Alternatively, we have written a C++ plugin which uses ROS to create a robot trajectory and then interacts with the VRAP scene to move the robot according to that trajectory. So you have various options here with different buttons. The next one is safety measures. Once the scene moves, you can tell VRAP to measure the closest distance between the robot and the worker, and you can program it to display it in red or orange according to a distance, which is if the robot and the human become closer than a certain distance you define. This is seen here on the right where the worker has an orange hand. This is another example of interacting between VRAP and the semantic scene map software. So in this case, we again use a simulated VRAP image and apply the semantic scene map Skeltonization algorithm to that image. And in this case, the skeleton is overlaid on the image, and this is visualized outside VRAP, just using the normal AVIS tool of ROS. But we went also another step further. In this case, we actually use a normal image from outside VRAP with a normal camera, apply the Skeltonization algorithm of the semantic scene map as seen on the left, and then using the plugin, another C++ plugin, use the coordinates of that skeleton and draw it inside the scene, inside this VRAP scene. So this way you could simulate or set up some test outside VRAP in the real world with a table and some working area, and then combine it with a robot inside VRAP. So here on the right you see the the human skeleton created from outside VRAP in the background, and the actual VRAP human is in the foreground. And you could move the background human closer to the robot. This is all configurable, and you can then simulate like a combination of a virtual scene and a real scene. Okay, this is it for the virtual design tool. Thank you very much.
Thank you very much, Martin, and would like to thank you for attending this webinar. I hope that has been interesting and full of inspiration and inspired you. And hope to see you again in a month with the final results of the Rossini project. Thank you very much. Have a nice day.